Good evening. We're Group 2 here to present our capstone project entitled Are We There Yet? Data Driven Insights for Local Government Traffic Management. Aside from losing our minds, our temper, and whatever it is that makes us good people, what else do we really lose whenever we're stuck at traffic? And the answer is 4.3 billion pesos per day. As a nation, 4.3 billion pesos per day is the total amount of economic losses incurred by Metro Manila's traffic. These losses can be in the form of inefficiency costs, like not enough goods are being sold due to transport delays, or it can be in the form of transport costs, like how your gas tank continues to dries up while you're in a standstill in EDSA. Either way, 4.3 billion pesos per day has better things to do than being stuck at traffic. But what if solving traffic is part of your job? Let's say that you work for an LGU and you're part of the team in charge of city traffic management. How would you go around solving this decades old problem? Our goal is to help you by building a dashboard that shows the projected hour per hour traffic in all of the streets in our area. A dashboard like the ones in front of the driver's steering wheel gives the user an overview of how well he or she is doing while driving. Depending on the goals of the driver, say to consume gas or move faster, these dashboards serves as both as a guide and a source of feedback that help the driver achieve his or her goals. To be clear, similar to how a car's dashboard alone is not enough to make one a good driver, our traffic dashboard by itself will not be able to immediately ease traffic nationwide. What it can do is to help LGUs be better drivers of change. This is done by making it easy to monitor progress and receive feedback, as well as by making the most pressing problems easier to identify.
So what is a dashboard? A dashboard is a way of displaying various types of data, visual data in one place. Usually, a dashboard is intended to convey different but related information in an easy to digest form, and here is an overview of how our dashboard looks like. A user needs to input the route, the date, and the time to show a projection of the traffic levels of the chosen route. From that, an individual can plan accordingly for his future travel. But for the who are going to use our tool, they can get a lot of insights from the generated graphs that will greatly help them in planning their city's road networks, transportation routes, and so on. And here's a prototype of our dashboard, currently deployed in Streamlit. From here, the user can have an overview of his whole journey with charts, network graphs, and even insights. Now, let's dive deeper into the development and the process our data has undergone to build our model and ultimately our dashboard. Due to Google Maps API's data limit, this project only focused on 3 of the most commonly used routes in Pasig City, and the data we collected only covered a 4-week period from December 5, 2022 to January 1, 2023. And another limitation of the API was that historical data cannot be collected. And so at the time of our data collection, we used future dates. Now that we have our data, let's look at the things we discovered in our exploratory data analysis.
So for our EDA, we first investigated the speed per week for each route, and we can see here, next slide please. We can see here that there isn't much of a difference in terms of average speed per week. But looking at the speed in weekdays compared to weekends for each route, we found that the speed for weekdays, morning and afternoon, are much lower than weekend. And weekday evening is just a bit slower than weekend evening. And moreover, we also found that the traffic usually happens every Friday for Pasig Palenque to LRT Santolan and Pasig City Hall to Kenneth, and Tuesday for Pasig City Hall to Ligaya. On the other hand, Sunday gained the fastest speeds for all routes. Next slide, please. Um, so for all routes, they are experiencing traffic during rush hour, especially at 6 p.m. Okay. So now let's move on to how we build our clustering model.
For our ML model, data was manipulated and transformed by adding new columns, segments, and speed, for example. Time of day and days of the week were categorized. We made sure that rows with NaN values were removed before reshaping the data with average speed values, with respect to the categorizations created beforehand. We then select a few features to be used: distance, which is the segment length, and still categorizing the data with average speed, whether speed is normal or traffic for each specific day group in a defined time frame. Pre-processing the data doesn't end with that. We then check for outliers in our data by creating plots for every features that our model has. And arguably, outliers are present in our data, and it was dealt with by using robust scalar. At this point, we aim to use k-means clustering. We then proceed to the next step, which is choosing the optimal k-value. We also try different measures, such as the elbow method and Kalinsky-Harabas score, which gave us 4 as the optimal k-value. And here's the result of our profiling using the distance, group of day, specific time of day, and categorized whether speed is normal or traffic, as well as the profiling results using segment length as distance. Cluster profiles were categorized this way. Cluster A, fast with normal speed of 9.6 meter per second during day and nighttime, with traffic speed of 10.6 meter per second during daytime and 9.1 meter per second during nighttime, with an average distance of 198 meters. Cluster B, average with normal speed of 6.7 meter per second during day and nighttime, with traffic speed of 7.3 meter per second during daytime and 6.5 meter per second during nighttime, with an average distance of 148 meters. Cluster C, slow with normal speed of 4.8 meters per second during day and nighttime, with traffic speed of 5 meter per second during daytime, 4.7 meter per second during nighttime, with an average distance of 108 meters. Lastly, cluster D, very slow with normal speed of 3 meter per second during day and nighttime, with traffic speed of same 3 meter per second during day and nighttime, with an average distance of 138 meters. For the results, I'll be handing you over to Jamil.
And now, let's apply the cluster labels into our original data and analyze further each route. In the pathway Pasig Palenque to LRT Santolan, we can see that the congested roads are in the middle and the southern part of the route, and the northernmost part is where the traffic is relaxed. Majority of the segments in Route 0 belong in Cluster B are the traffic segment identified with average speed. This route has the most efficient network of segments among the 3 studied routes, as it has the lowest number of segments under Cluster D. For Pasig City Hall to Kenneth, it has no blue lines, which means that its segments could be congested. So let's take a look at the distribution. And there we go. Route 1 segments are predominantly congested with slow to very slow traffic. And in terms of distance, 57% of the commuter's journey will travel on roads with very slow traffic. Lastly, for Route 2, it was identified that its middle part is where the traffic is at easiest, as indicated by these blue segments. But the rest of it mostly under the cluster C and D, as shown by the yellow and red lines. And same as the previous route, most roads in Route 2 are in the categories of slow to very slow clusters. At this point, we have established what we can get from the dashboard. So now, what can we do with it? Some of our recommended applications include: first is for forecasting traffic for future travels. Users of the dashboard can plan wisely their future travels, such as which roads to take and which ones not to take, with the help of our clustering model. In addition, with the travel duration feature of the Google Distance Matrix API, the users can determine the estimated travel time days from now, weeks from now, or even months from now. And with that, they can plan accordingly and avoid inconveniences due to traffic such as transport delays and late arrival in important meetings. Another use, especially for LGU's traffic management units, users can create new routes for their shuttle services or free bus rides for their constituents. From the network graphs, they can even identify which of the pathways they are currently using are inefficient, and they can reroute accordingly by avoiding the segments in red. As mentioned earlier, our dashboard is just a prototype and a proof of concept, and admittedly, it needs improvements. And to address the gaps identified, the LGU or any other organizations interested with our study can provide financing of the API to increase the data capacity and add more segments in the data. Secondly, they can innovate this idea and include historical data to incorporate reinforcement learning, which may optimize the model. And that concludes our presentation. Thank you for listening.